Hello, and welcome to this Hermetic Solutions Group webinar. And now I would like to introduce today's presenter, David Dwyer. As the Vice President of Business Development for Hermetic Solutions Group, a company comprised of 6 business units located worldwide that are focused on providing engineered products, services, and device packaging solutions to leading suppliers of the global defense, aerospace, medical, energy, and telecom markets. David, welcome to today's event. And with that, I'd like to pass things along to you to get us started. Go right ahead.
Hello and welcome. Thanks for joining us today. My name's Dave Dwyer. I'm the Vice President of Business Development for Hermetic Solutions Group. Today's webinar is titled Filling the Gap in Passive Thermal Management. Here's a brief rundown of today's presentation. I'm going to talk about Hermetic Solutions Group, give you an idea of who we are and what we do. Then I'm going to introduce this new novel passive thermal management material to you. I'm going to talk a lot about the test methodology that went behind the characterization and qualification of the material. And then lastly, give you some observations, things discovered during the testing of this material. So regarding Hermetic Solutions Group, we're a company of about 650 employees operating at 7 locations around the globe. Our Pacific Aerospace Group that you see here on the left-hand side of your screen is located in Wenatchee, Washington, and they manufacture hermetic packaging, feed-throughs, and connectors for mill aerospace applications and medical devices. Our Sinclair Group, located in Norton, Massachusetts, manufactures hermetic packaging using glass seals, soldered feed-throughs. They manufacture window assemblies and other components related to the hermetic package business. Our Hi-Rel Group is made up of 3 different facilities. Our Hi-Rel Products Group located in Essex, Connecticut, our Hi-Rel Lids Group located in the UK, and our Hi-Rel Alloys Group located in Niagara Falls, Canada. At Hi-Rel, we manufacture all the enabling components that make up hermetic packages. Things like alloy preforms, thermal materials, lids, getters, and we're able to add all of those into a combo format, a lid that has preforms, getters, absorbers attached to it. At our Litron facility located in Agawam, Massachusetts, we do laser services there. We manufacture medical devices, both Class 2 and Class 3 devices at that facility. We do laser services there. We are able to weld hermetic packages in our ISO Class 7 clean room. And we also manufacture glove box laser systems for sale to our customer base. So when I joined Hermetic Solutions Group roughly 2.5 years ago, I wanted to spend some time with our customers and really sit down with them and understand what were the challenges that our customers were facing. What were the dynamics of their business? What were the things they needed to get more out of their devices? And as I sat down and looked at my notes after all these visits, thermal management rose to the top of the list. Certainly, with the advent of new wide bandgap technologies, devices like GaN, silicon carbide, the need for greater thermal management really rose to the top. Secondly was the gettering of unwanted gas species with a removal of hydrogen and moisture from hermetic enclosures. And lastly was EMI RFI shielding. Today we know that roughly 50% of electronic failures are due to thermal issues, and that oftentimes thermal challenges can directly affect and limit device performance. You just can't get the right architecture to get all the power out of some of these new wide bandgap technologies. And certainly with design constraints, trying to attain smaller form factors coupled with higher frequency and higher power density really challenges the designer in thermal management. And a lot of products today, particularly in the mil aerospace market, have space limitations and that limit access to convective cooling architectures. There's just no room to get the heat to sweep the heat away. And for sure, there are limitations of legacy conductive thermal materials, and we'll talk more about that. So when you look at device technology that's existent today, on the left-hand side, you'll see a silicon wafer that's long been the mainstay of semiconductor device technologies. Uh, but as the need for higher frequencies started to drive the limits of silicon, gallium arsenide came into play. Gallium arsenide is very friendly to higher frequencies. And then the need for higher power devices came into play, higher power devices that could manage higher frequencies. So products like silicon carbide were developed. And most recently, this great wide band gap material, GaN, gallium nitride, is becoming more and more the mainstay, the go-to semiconductor device technology in the world. The chart below on this slide, by the way, is courtesy of Analog Devices, is a great representation of where these device technologies sit in that power to frequency curve. You can see that silicon still has a real strong base in products like laterally diffused MOSFETs, products that can handle very high power up to 1,000 watts, but is limited in frequency to around roughly 2 gigahertz. And you can see silicon germanium and gallium arsenide are kind of the province of lower power devices that, 5-watt kind of devices and lower, but handle very high frequencies up to about 100 gigahertz. And new to the party, you can see gallium nitride has started to take a big bite out of this curve. Gallium nitride and silicon carbide are very friendly in this high power dense universe and are starting to work in frequencies up to 100 gigahertz, working in that millimeter wave realm. So let's talk about the types of thermal management. If you were to ask 10 different people what they thought thermal management was, you'd probably get 10 different answers. So what I want to show here on this slide is kind of define where this new novel material sits in the thermal management space. On the top of this slide, you'll see active thermal management products, things like Peltier coolers and chillers and condensers and chill plates that are very widely used where access to power and fluids will work in an application. At the bottom of this slide, you'll see the passive thermal management space. And this is really where we're headed in this presentation. This is what we're going to talk about. And you can see materials that have long been sitting in this space, things like AlSiC, things like copper moly, copper tungsten. New to the party, certainly freestanding diamond with very high thermal conductivity. And then some surface mount products like pin fins with thermal interface materials. So on this slide, you'll see different images of ways to manage thermal energy. In the top left, there's a chip scale BGA cross section. This device technology essentially requires that thermal energy be removed through the lid of the device. Down on the bottom of this slide, you'll see a power IGBT where a significant amount of thermal energy needs to be dissipated through multiple layers of these packages. In the upper right, this is really where we're going to talk about today. This is a heat spreader technology, essentially where a die is mounted directly to a heat spreader. And we're going to discover how this new novel material behaves in this application. Just stepping away from those cartoon images for a minute, going to show you some actual devices here, kind of where that heat spreader technology could play. In the upper left, you see a power RF package. Down on the lower left, you'll see a multi-layer ceramic package with a heat spreader and die mounted to it. On the lower right, you'll see laser diode packaging, things like laser diode submounts where these passive thermal management materials can play. And in the upper right is a standard flat pack, again, where these thermal tabs could play. The picture you see here in the center is just kind of an up-close view of a heat spreader, and mounted directly under the die, mounted to a heat sink. And that's really what we're going to talk about in this presentation. So to further define the passive thermal management space, I put this slide together just to give everybody an idea of kind of where we play. In the passive space, there's really two basic kinds of product. There's the non-electrically conductive types of materials, things like ceramic, and then there's the electrically conductive materials that you see at the bottom of this slide. We're going to be talking about this electrically conductive space in this presentation. So when you take those electrically conductive heat sink materials and put them on a price to performance curve like I'm showing here, you can see that all those materials are kind of grouped in that sub 200 watt per meter K thermal range. Now I did take some liberties here with the price per cubic centimeter, so that's kind of immaterial to the purpose of this slide. On the far right-hand side, you'll see a piece of electrically conductive diamond, this boron dope material that is both electrically conductive and also has very high thermal conductivity, in this case, up as high as a couple thousand watts per meter K. But if you look at this slide, you'll see that there's this huge gap in the middle of materials that are commonly available. From the legacy materials on the left-hand side to the new kinds of products, this freestanding diamond that's on the right-hand side, there's really nothing in between. And that's what we're going to talk about here today. So when we looked at ways, technologies to fill in that gap that we saw on the previous slide, this chart came to mind, and I'd remembered it from many other presentations I've seen over many years. It's a great chart, and kudos go out to whoever originally put this together. But it's a great depiction of where materials, both native and composite and laminate materials, sit in the thermal conductivity to thermal expansion coefficient curve. The products that you see here highlighted in red are the non-electrically conductive materials, things like BEO, alumina, silicon nitride. The native materials you can see here are silver and copper and gold and aluminum, things like that. And also the laminate structures, the alloy materials, the metal matrix composite materials like copper tungsten and copper moly and copper moly copper are all shown here. But additionally, I've added now the diamond-based composite materials, copper diamond, aluminum diamond, and silver diamond that you'll see at the upper part of this chart. And that's really what I looked at to fill that gap in that thermal management space we talked about in the previous slide. So what's our solution? So this is our solution. This material that you're seeing in this image is our Diacool material. Diacool is a trademark name that represents metal matrix composites built using diamond in the matrix. Now, in this case, Diacool could mean copper diamond, as you see here, or aluminum diamond, or silver diamond. All fall under that Diacool trademark name. The material is made in large area sheets like you see here. In this case, these plates are all 150 millimeters square, or in English, roughly 6 inches square. So how is Diacool manufactured? In the upper left-hand picture of this slide, you'll see bulk diamond powders. These are synthetic diamond crystals that have been grown in a lab to be used in this application. We take those bulk diamond powders and enhance them by adding constituents to the surface of those diamonds to help them adhere to the metal part of to make up this matrix, be it aluminum metals or copper or silver. Then we take those diamonds that have been enhanced and mix them with pure copper powder and place them in a mold cavity that you see here in the third image from the left. And that mold cavity is essentially a graphite tool that can be in any shape or size. And the material is placed into this mold cavity. And then in the final step, the material goes into a hot press where it is condensed, held under very high pressure and high temperature to essentially create this cake, the matrix that makes up the core of Diacool. The image that you see here at the bottom is just a kind of a cartoon image of how the material is put together. In step one, you'll see this the matrix suspended between two layers of pure copper. So after the material is pressed and sintered into a cake, we add pure copper sheets to both sides of the substrate. And in another hot pressing step, we force that copper skin on both sides of the cake material. That's that matrix part of the substrate, and press them together to form a single bonded unit from top side to bottom side. And then in the last process step, we can machine this material to either add structures or to reduce the thickness of the copper on both sides of the substrate in order to make it more friendly to device and die attach. So when you take this Diacool metal matrix composite material and test it for CTE, you get these kinds of results. You can see in this chart where I've measured this material over a broad range of temperature from essentially room temperature up to 475 degrees C. And I've looked at the coefficient of thermal expansion of various lots of this material. The tan bar that you see here is essentially just put there to represent the kind of the operating temperature of most device technologies today. And you can see in all cases that this material has a very friendly coefficient of thermal expansion that sits right around that 6 to 7 ppm kind of range. So likewise, of course, I wanted to look at the thermal conductivity of this material. The chart you see here in front of you represents temperature range of essentially room temperature up to 400 degrees C. Again, that tan box represents typical operating temperatures of devices today. And you can see that this material has high thermal conductivity of around 415 watt per meter K up to about 480 watt per meter K in that operating temperature range. So understanding that the structure of this material could have an effect on the testing of its thermal conductivity, the fact that it's not homogeneous from one edge to the other made me think that we needed to look at this a little differently. So I considered the omega-3 test methodology that effectively takes a sandwich structure of material like this and breaks it down into its constituents. In the case of the chart you see here in front of you, I tested this material over a range of room temperature up to 300 degrees C. Again, that tan bar that you see, or that tan box, kind of represents operating temperatures. So if you look at this chart and take it, let's look at it from the bottom up. That blue bar that you see at the bottom essentially takes the copper skin that's on both sides of this material and tests that skin by itself. And you can see it behaves very much like copper should. At room temperature, the thermal conductivity is around 400 watt per meter K. The next two bars that you see moving up the chart represent the thermal conductivity of the whole structure being that copper diamond matrix with the sandwich of pure copper on both sides. And in this case, there's two bars, one designating thermal conductivity in the Z direction and the other in the planar or X and Y directions. And you can see the material has high thermal conductivity, in that 490 watt per meter K down to 425 watt per meter K that we actually saw in some earlier slides. Now, interestingly enough, the orange bar that you see on the top represents the matrix itself, that copper diamond matrix, essentially scrubbing away the copper that exists on both sides of the matrix and looking just at the matrix itself. And you can see that the effect that the diamond has on that copper, showing us that the material has thermal conductivity up to 550 watt per meter K at room temperature down to roughly 500 watt per meter K at 150 degrees C. So all of us understand that we need to know how this kind of material will stand up to the rigors of thermal cycling. In the case of the chart in front of you, you can see where I took materials from the same lot of material and tested them without thermal cycling and then again with thermal cycling. Now, by the way, this test was completed using a laser flash technology that exhibits lower coefficient of thermal expansion because of that non-homogeneous nature of the material. But you can see here in the chart on the top left, I took substrates of this material and tested them from 50 degrees C up to 300 degrees C with no thermal cycling. And you can see the material sits in that 350 watt per meter K range over the course of that temperature range. Then I took those products and I thermal cycled them using conditions like Mill Standard 883, Method 1010, Condition B, and thermal cycled this material for 60 cycles and then tested the material again. And that's depicted in this chart down on the lower right. You can see that there's very little difference between the two. The difference is minimal, roughly around 5%, essentially, if you will, a settling in of this material. And as I tested this material even past 60 cycles, I saw no degradation of thermal conductivity even beyond 100 cycles. So the material is very stable in these kinds of cycling conditions. So I wanted to test how electrically conductive this copper diamond Diacool product is. And in the chart that you see in front of you at the top part of the slide, you'll see the volume resistivity measurements in ohms per centimeter, right around 6. This material is essentially 45% copper, so electrically it behaves very much like copper and is very uniform in conductivity in all directions. At the bottom part of this chart, you'll see the density of the material. In this case, density in grams per cubic centimeter. You can see across the curve, this product sits right around 6 grams per cubic centimeter. Just as a point of reference, copper is around 9 grams per cubic centimeter. So the next thing I was interested in looking at in the qualification of this material was how well that copper skin that's being hot pressed into the copper diamond matrix, how well it adheres to that copper diamond matrix. So I had SEMs done of the material, and the pictures that you see here in front of you are representative of those SEMs I had completed. And looking from the top to the down to the lower right, you'll see different cross sections of the material, different backscattering methodologies that we use to look at the material. And in all cases, you can see the material is that there are no boundary layers between that skin and the matrix. It's a very uniform and consistent kind of process that allows that material essentially to blend with the copper diamond matrix. The image you see here in the center just gives us a cross-sectional view of both sides of the substrate so that you can see how effective the material adheres on both sides of the matrix. So one of the tests that we use to help us engineer and evaluate this material is the use of this high-intensity flash lamp. You can see here in this blue image on the left-hand side of this slide, this is essentially a fixture that has these high-intensity flash lamps distributed across the surface of that fixture. And in this case, we take these substrates of diacool and place them into this flash lamp and flash the material and take an image, a thermal image that tells us the thermal diffusivity of the material depicted here on the right-hand side in this green image. So by taking this essential thermal map of this material, we can tell how uniform the material is distributed, how well the material has coalesced. And we can look at this with an eye to creating materials that are uniform in nature and have good distribution of thermal conductivity across a substrate that's as large as 150 millimeters square. So now we're going to take a look at this diacool material and see how it performs thermally in comparison to traditional legacy material like copper moly and just a piece of pure copper. So what you see here in front of you is an image of three different substrates of material that are all of the same form factor, same length and width and thickness. In this case, these samples were prepared with a resistor mounted on the back side. And in all cases, these samples are just sitting out in open air. There is no thermal platform that these are mounted to. And we applied thermocouples to the same area of each of the three substrates. Now what we're going to do here in this test is we're going to fire up those resistors on the back side of these substrates and take a thermal image of the three substrates of material and see how they manage that heat flux generated by the resistor. So you can see the temperature starting to rise. You start to see a significant hotspot develop on the copper moly sample. And now you can see a large hotspot appear in the copper sample. The interesting thing to look at here is the thermal gradient across the three substrates. So moving from the left, look at the copper sample, you'll see that there's a thermal gradient of around 3 degrees centigrade from the center of the part on the opposite side of that resistor to the edge of the part. But you can see a significant hotspots developed in the center of that substrate. Over on the right-hand side, the copper moly sample has a very large area, hotspot area. But more importantly, you can see the lack of thermal spreading of this of the copper moly material. You can see a thermal gradient here of around 10 and 11 degrees centigrade from the edge of the substrate to the center. Where in the middle, this diacool product line shows very even thermal flux across the entire substrate, and there is essentially no thermal gradient. depicting that this material is a very effective heat spreader both in X, Y, and Z directions. So how do we prepare this material for consumption? These large area substrates of Diacool material can be wire EDM'd, they can be laser cut, as you see here in the two images on the left-hand side of this slide. The material can be cut into any shape or size. There's really no limits to the kinds of geometries that we can create with this material. It also is, because it's largely copper, it plates very much like copper and is friendly to any kind of plating chemistry that you can imagine. The images you see here of electrolysis nickel and gold-plated parts and sulfamate nickel and gold-plated parts are just examples of the kinds of chemistries you can use on this product. We can also add any pig or any other chemistries that you may consider. In this slide, I wanted to show you how this material is made available to our customers. In all cases, we take this product, these large area substrates of material, and cut them up into individual heat sinks. The image you see here on the left-hand side is just a cross-sectional view of the material, kind of what it looks like in its as-pressed state. And I put this image here just to give you an idea of how it looks in that cross-sectional view. The image on the right-hand side has had the copper removed from both sides of the substrate, removed down as close as possible to that copper diamond matrix. And the other advantage of this process is that it allows us to add very thick skins of material to this matrix, such that we can effectively structure a surface, machine a structure into the surface of this product, as shown here in this picture in the center. In this case, this is a large substrate, roughly 6 inches long, 4 inches wide, where we have machined a pin-fin heatsink into the top surface of this part. So this nearly concludes today's presentation on Diacool. However, I wanted to show you this video that gives you a little different viewpoint of how well Diacool acts as a passive thermal spreader. In the case of this video, I'm going to show you two samples of material, one being a pure copper sample and one being a copper diamond Diacool sample. In this case, I've got a resistor mounted to the backside of two identically sized substrates, and I'm going to fire up that resistor. And the idea here is to see how long it takes this product to thermally dissipate up to 80 degrees C and then cool down to around 50 degrees C. So to conclude today's presentation, we recognize that heat stress is the #1 failure mode in electronic systems today. We also found that legacy passive thermal spreaders are just not keeping pace with the evolution of semiconductor device technologies. In fact, these legacy thermal spreaders can be restrictive to the designer realizing the full potential of these new wide bandgap device technologies. We also saw that new diamond metal-based metal matrix composites do have the ability to fill the open space, that big gap that exists in the price to thermal performance curve today. And we also know by looking at the testing that went on in this case that the material and the technology is robust. I would like to acknowledge some contributors to today's presentation, certainly my colleague, Dr. Waji from Hermetic Solutions Group, the folks out at PMIC, third-party test lab located in Corvallis, Oregon, and my friends at NCSU that helped me through the omega-3 testing. And certainly, last but not least, our thanks to the Global Spec team for hosting a great webinar. So that concludes today's presentation on filling the gap in passive thermal management. I'd certainly like to thank all of you for joining us. I hope you've enjoyed this presentation as much as I've enjoyed giving it. I'm going to open up the floor now to any questions that you may have.
David, thank you so much for that great presentation. We do have some questions that have come in from our attendees, so we are going to move into answering those right now. Now, our first question. Can this material be traditionally machined using carbide tooling?
So that's a great question and one I face a lot. No, unfortunately, this material cannot be traditionally machined using carbide tooling. That diamond matrix composite material is really hard, and the only effective way to cut this material is using wire EDM or laser cutting, as I've shown in some of the previous slides.
Okay, great, thank you. What type of plating chemistries can be used on this material?
So really, this material can be plated using any chemistry the designer may wish. It is copper, so it takes really well to any plating chemistry you can imagine, from electroless to electrolytic materials to any pig. Really, it's up to the designer.
Okay, David, another one here for you. How do the edges of the material appear after cutting?
After cutting, the edges of this material will show that sandwich structure that I showed earlier. It is a relatively smooth edge. The grit size of the diamonds used in this composite are very small, so you can see some roughness, but after plating, oftentimes this material is very smooth and shows a smooth transition from the top surface of the material down the edge.
Okay, great. Thank you, David. Another one. What is the surface roughness of the die attach area?
So that's a great question too. The surface roughness of the die attach area is as smooth as it is structured by Hermetic Solutions Group. It is essentially a pure copper die attached surface, so we can structure the surface roughness to be pretty much anything that a customer requires.
Okay, great. Thank you. Is the material available in net shape?
Yeah, that's a great question as well. The material is available in net shape. This material can be put into a formed mold and create different walled structures, if you will. So it is available in net shape. However, it does require custom tooling to manufacture those kinds of products.
Okay, David, I think this is going to be our last question today. How does the cost of this material compare to legacy technologies?
Well, this is a question I get a lot. This material, a good way to look at this material is it's not copper and it's not diamond. It is more expensive than than current legacy technologies, really as a result of its being new to the market. Um, the cost to manufacture it is low. And you can see, as I've shown in earlier slides, this material is made in large area sheets. So you get the benefit of quantity of product per plate.
All right, great. Thank you so much for answering all of our questions. We are going to wrap up the webinar right there. David, thank you so much for taking time to be here with us today. And I want to say thank you to all of our audience members for being part of this webinar event. Take care, and we will talk with you soon.